Did you know that millions of gallons of juice get made in factories at a scale you've never witnessed before? These machines single-handedly carry the juice industry, and without these insanely complex processes, we would not be drinking it. Today, we're diving deep into how orange, apple, and mango juice get produced using revolutionary methods. Orange juice production in a factory begins with the arrival of fresh oranges in massive quantities, typically delivered by trucks carrying bins or crates that can hold thousands of pounds of fruit. The oranges are poured into large hoppers and then guided along a vibrating conveyor system that helps to separate any debris such as leaves, twigs, or clumps of soil. As the fruit moves forward, it passes through an initial rinse system where pressurized water jets spray away surface dirt and residues. Rotating drum washers further agitate the oranges, scrubbing them gently with food-grade brushes to ensure the peels are completely clean before any juice extraction begins. Once washed, the oranges travel up an inclined conveyor that feeds into a mechanical grading line. This line uses a series of rotating rollers with increasing gaps that allow smaller or misshapen oranges to fall through and be separated from the main batch. Optical sorting systems are often installed here as well, using cameras and infrared sensors to inspect the surface quality and color of each orange. Damaged or underripe fruit is ejected automatically by a timed air puff system. Only high-grade oranges make it past this point, continuing along the line toward juice extraction. Next, the sorted fruit enters the sizing stage. Here, the oranges are divided into different lanes based on diameter. This ensures that each juicing unit receives fruit of uniform size, which helps maintain consistent yield and reduces strain on the equipment. The oranges are guided into feed channels that position them directly into the juice extractors. These machines are highly specialized. They operate by slicing the orange in half and then pressing each half against a conical reamer, while simultaneously filtering out seeds and peel fragments. Some systems use a piston and cup configuration, where a whole orange is pressed between a domed upper cup and a lower cutting tube that pierces the peel and squeezes out the juice under high pressure. The extracted juice flows downward into stainless steel collection pans beneath the extractor units. At this point, it still contains pulp, peel oil, and small fibrous fragments. The juice is directed through a coarse mesh screen that removes large solids, then flows into a centrifugal separator. This machine spins the juice at high speed inside a cylindrical drum, using centrifugal force to separate pulp and heavier particles from the liquid phase. The resulting juice is brighter and clearer, but it is still far from ready for bottling. From here, it enters a balance tank that acts as a buffer, feeding the next process continuously even if there's a brief pause upstream. The juice is then pumped toward a heat exchanger for pasteurization. Before entering, the juice is measured for its Brix level, the concentration of dissolved sugars, using inline refractometers. This allows technicians to ensure the juice meets sweetness specifications. As the juice enters the heat exchanger, it flows through a system of narrow stainless steel tubes that are heated externally by hot water or steam. The juice is quickly brought up to a pasteurization temperature, typically around 90 degrees Celsius, for a brief period of time, often under 30 seconds. This short heat burst is enough to kill off any harmful microorganisms or enzymes that could cause spoilage without damaging the fresh taste of the juice. After pasteurization, the juice is rapidly cooled by a regenerative cooling loop where the incoming cold juice cools the outgoing hot juice through thermal exchange. This keeps energy usage efficient while ensuring that the juice exits at a safe and stable temperature, usually just above freezing. The cooled juice is then stored in large, chilled stainless steel holding tanks. These tanks are equipped with slow-moving agitators that keep the juice uniformly mixed and prevent settling. The tanks are sealed and often nitrogen purged to reduce oxidation and preserve flavor during this intermediate stage. Depending on the product being made, this base juice can now follow different paths. For not from concentrate orange juice, the liquid moves almost directly to packaging. For from concentrate production, the juice is sent to an evaporator system. Here, the water is removed by gently heating the juice under vacuum conditions, allowing water to evaporate at a much lower temperature than normal boiling. The result is a thick, syrupy concentrate with only about 1/6 of the original water content. This concentrate is easier and cheaper to store and ship, and later in the process, it will be reconstituted by adding purified water back in to reach the original volume and consistency. Regardless of the juice type, another critical step occurs in parallel: flavor recovery. When juice is extracted and pasteurized, volatile aromatic compounds are released into the vapor phase and lost unless captured. A dedicated flavor recovery unit condenses these vapors and separates out the essential oils and aroma compounds, which are stored in small, sealed vessels. These recovered flavors are later added back into the juice, either before packaging or during the reconstitution stage, to restore the characteristic citrus profile that would otherwise be dulled by processing. In the case of juice with pulp, a controlled amount of pulp is reintroduced into the clarified juice. The pulp is collected from earlier filtration stages, passed through a sterilization step, and dosed into the juice stream in precise proportions. Flow meters and mix tanks ensure that every bottle or carton has uniform pulp content throughout the batch. With the juice now stabilized, flavored, and standardized, it moves to the final filtration and deaeration stage. Fine filtration using microfilters ensures that no residual particulates remain in the juice. Deaeration systems use vacuum chambers to strip out dissolved oxygen from the juice, which helps extend shelf life and reduces oxidation of flavor compounds. The oxygen-free juice is now ready for final packaging. The packaging system begins with bottle or carton sterilization. Empty containers are passed through a sterile air tunnel or sprayed with a sanitizing agent like hydrogen peroxide. They are then rinsed and dried before entering the filling machine. The juice is filled into bottles using positive pressure or gravity fillers in a sterile chamber with HEPA-filtered airflow to prevent microbial contamination. Each bottle is filled to exact specifications, checked by weight sensors or laser volume detectors, and immediately capped with a tamper-evident closure. The sealed bottles proceed through a cap sterilization tunnel and then into a final pasteurization or hot water shower, depending on the product's distribution requirements. After this thermal stabilization, the containers are labeled by high-speed machines that apply shrink sleeves, wraparound labels, or printed adhesive labels depending on format. Inkjet printers mark the production date, expiration date, and batch number on the cap or neck. The bottles are then grouped into trays or shrink-wrapped into multi-packs. These are placed onto pallets in a programmed stacking pattern optimized for load stability and storage efficiency. Robotic arms or palletizers stack the packs, and each pallet is wrapped in stretch film and affixed with a shipping label that includes traceability codes. The pallets are then transferred to refrigerated storage areas where the temperature is tightly maintained to keep the juice fresh before distribution. Every stage of the process is monitored by a centralized control system that collects data from sensors embedded throughout the line. Flow rates, temperature curves, pressure differentials, pH levels, and oxygen content are all tracked in real time. If any measurement drifts outside of specified limits, alarms are triggered, and corrective actions are taken to ensure product quality is never compromised. Quality assurance teams collect periodic samples for laboratory testing, checking not only microbial safety, but also taste, color, texture, and chemical composition. Apple juice production in a factory starts the moment large shipments of freshly harvested apples arrive at the intake area, usually packed in massive crates or bins and unloaded using hydraulic tippers. These bins are emptied into stainless steel flumes filled with cool water, which not only begins the cleaning process, but also allows the apples to float gently through the first stages of sorting, protecting the fruit from bruising during transport within the facility. As the apples flow forward, debris such as leaves, twigs, and stones sink and are swept away by underwater conveyors, while the fruit continues toward a mechanical washer that begins the first rigorous stage of surface cleaning. This washer is a rotating, cylindrical drum lined with flexible food-grade brushes and multiple rows of spray nozzles. As the apples spin inside, high-pressure jets of filtered water remove stubborn soil while the brushes scrub the skin evenly without damaging it. This continuous rotation ensures that every surface of each apple is exposed to water and mechanical contact. Exiting the washer, the apples are carried by vibrating dewatering conveyors, which shake off excess moisture and direct the fruit to the optical sorting line. Here, the apples are spaced evenly using mechanical aligners and pass through a tunnel equipped with multi-angle cameras, hyperspectral sensors, and infrared lasers. These technologies analyze surface color, size, shape, and even internal density, allowing the system to detect defects like bruising, rot, or underripeness. Any apple failing the programmed quality thresholds is automatically diverted via precision air jets to a separate path, while the rest proceed to the crushing station. The qualified apples move onto a conveyor that delivers them into a hammer mill or blade grater, which tears them apart into a coarse pulp known as pomace. This mash is made of juice, flesh, skin, seeds, and stems, and is held temporarily in an agitated holding tank to ensure uniformity. The mash is then pumped to a pressing system, often a belt press or pneumatic bladder press. In the belt press method, the mash is sandwiched between two porous synthetic belts that travel between a series of rollers. These rollers gradually increase in pressure, squeezing the juice out of the mash through the belts, while the dry pulp, now significantly reduced in moisture, is scraped off and collected for animal feed or compost. The freshly pressed juice flows into a stainless steel catchment pan and is pumped immediately to a clarification system. At this stage, the liquid is cloudy and filled with suspended solids, primarily made of pectin, starch, and fine plant cells. To remove these, the juice is first treated with a pectolytic enzyme in a stirred tank, breaking down the pectin structure that holds the solids in suspension. After a short incubation period, the juice is pumped into a centrifuge. This high-speed rotating drum forces the heavier particles to the outer wall, allowing the clarified juice to collect in the center. Separated solids are removed continuously from the edge and sent to waste collection tanks, while the juice is directed toward a fine filtration system. In the filtration phase, the juice is passed through multi-stage filters, often plate and frame or cross-flow membrane units that remove particles down to the micron level. The result is a clear, amber gold juice that retains its flavor and brightness while improving shelf stability. From here, the clarified juice is moved to a pasteurization unit via sanitary-grade stainless steel piping. Inline refractometers measure the Brix level of the juice, which indicates the concentration of natural sugars, ensuring each batch falls within the desired sweetness range. Pasteurization is then carried out by pumping the juice through a tubular or plate heat exchanger, where it is rapidly heated to approximately 88 to 90 degrees Celsius for about 30 seconds. This quick, high-temperature exposure inactivates enzymes and destroys any remaining microbial life without altering the flavor or nutritional profile of the juice. Following pasteurization, the juice is flash-cooled using a regenerative system in which outgoing cold juice pre-cools the incoming hot juice, reducing energy consumption while preparing the product for storage. The cooled juice flows into large, sealed, chilled holding tanks with internal paddles that slowly rotate to keep the contents uniformly mixed. These tanks are fitted with oxygen sensors and nitrogen purge systems to minimize oxidation, preserving color and taste. The juice remains here temporarily before either going directly to packaging or being routed through a concentration line. For juice products made from concentrate, a portion of the pasteurized juice is sent to a vacuum evaporator. This multi-effect evaporator reduces the juice under low pressure conditions, allowing water to be removed at relatively low temperatures and preventing thermal degradation. The juice becomes a thick syrup with 1/5 or even 1/6 of the original volume, rich in flavor and sugars. This concentrate is chilled and stored in sealed containers or frozen in large drums until needed. To reconstitute, purified water is added back in precise ratios using inline blending systems, guided by sensors that measure Brix, acidity, and flavor markers. Throughout the process, volatile aroma compounds that were lost during pressing and pasteurization are captured in a flavor recovery unit. This system condenses steam and vapor released during juice handling and separates the desirable aromatic fractions. These recovered flavors are later added back to the juice in the dosing stage to restore the authentic apple profile that might have been muted by heat treatment. The flavor dosing step is conducted just before packaging, ensuring that the final product retains its freshness and natural character. The next step is deaeration. The juice, whether from concentrate or fresh pressed, is transferred to a vacuum chamber where dissolved oxygen is removed. Oxygen in the juice can lead to discoloration and off flavors over time, so the vacuum deaerator reduces this risk while extending shelf life. Following this, the juice is passed through a final sterile filtration system that ensures it is free of any remaining particulates or microbial contaminants. Now fully processed, the juice proceeds to the filling line. Here, sterilized bottles or cartons are fed into a sterile chamber, often using an airlock or overpressure system with HEPA-filtered air to prevent airborne contamination. The juice is filled into containers using gravity fillers or pressurized nozzles that match the flow rate to the container size. Fill levels are monitored in real time by sensors and load cells, and any underfilled or overfilled containers are rejected automatically. Immediately after filling, each bottle is capped and sealed. Caps may be steam vacuum sealed or induction sealed depending on the packaging format. The seal ensures tamper resistance and microbial safety. Bottles then pass through a cooling tunnel or water spray cascade to bring the product temperature to storage levels. A high-speed labeler applies branded labels, while laser printers mark each bottle with a production date, expiration date, and batch identification code. These codes are linked to the factory's ERP system, allowing every bottle to be traced back to the exact origin and processing conditions of the apples used. Once labeled, the bottles are grouped into multi-packs or trays, shrink-wrapped, and placed onto pallets. Robotic palletizers stack the cases according to programmed patterns optimized for stability and transport efficiency. Each pallet is wrapped in stretch film, labeled with its batch data, and assigned a position in the cold storage warehouse. Inside the warehouse, temperature is carefully maintained and monitored, and inventory is managed with barcode scanning and automated tracking systems. When orders are placed, pallets are retrieved, scanned, and loaded onto refrigerated trucks using guided forklifts or automated shuttles. Mango juice production in a factory begins with the unloading of ripe mangoes delivered in large crates or bins that can weigh several hundred kilograms each. These bins are emptied into a receiving chute where the mangoes are guided into a flotation tank. This tank is filled with clean water, allowing the mangoes to float and separate naturally from heavier debris like stones, dirt clumps, or leaves. The floating system helps prevent bruising while also initiating the cleaning process. Submerged conveyor belts or rotating paddles gently propel the mangoes through the tank. From there, the fruit is lifted by inclined belts and directed toward a high-capacity washing machine. The washing machine consists of rotating, soft bristled brushes and high-pressure water jets arranged in multiple stages. These brushes scrub the mango skins, while the jets remove dirt, surface residues, and any traces of pesticide. The rotation and brushing ensure that every mango is cleaned thoroughly on all sides without causing damage to the fruit's flesh. After this stage, the mangoes pass through a rinsing tunnel where filtered water gives them a final clean before they're ready for sorting. Once cleaned, the mangoes travel along a vibrating dewatering belt that removes residual water, then onto a grading and sorting line. Optical sorting systems equipped with multispectral imaging cameras analyze each fruit's size, shape, and color. Defective fruits showing signs of rot, underripeness, or physical deformities are automatically ejected using targeted air jets. The remaining mangoes, now considered processing grade, are transferred to the peeling and destining area. Unlike apples or oranges, mangoes require more complex handling due to their fibrous flesh and large central seed. The mangoes first pass through an inspection belt where their orientation is corrected for proper alignment. They then enter a peeling machine equipped with abrasive rollers or sharp rotating blades that remove the outer skin. In some configurations, steam peeling may be used, where the mangoes are exposed to high-pressure steam for a few seconds, causing the skin to loosen and making it easier to remove with rubber rollers. After peeling, the mangoes are fed into a destining unit. This destining system is designed specifically to handle mangoes. As the fruit enters, it is squeezed against a grating or sieve by rollers that force the pulp and juice out through the mesh, leaving the large stone behind. These stones are ejected and collected for disposal or further processing in separate streams. The extracted pulp, still containing fibrous strands and varying in consistency, is collected in stainless steel tanks equipped with gentle agitators that keep the mixture homogeneous. At this point, the mango pulp is thick and viscous with varying amounts of fiber depending on the mango variety. To refine the texture, the pulp is sent through a pulping and refining line. First, it enters a pulper equipped with rotating blades that shear the pulp and reduce the fiber size. It then passes through a finisher or decanter centrifuge that separates out any remaining coarse fiber, unbroken skin fragments, or seed residues. The resulting puree is smooth, thick, and uniformly textured, ideal for juice production. This puree is stored in chilled, sealed holding tanks to await further processing. Next comes the standardization phase. Mango juice requires specific sweetness and acidity levels to maintain product consistency, especially when fruit quality and ripeness vary. The puree is transferred into blending tanks, where it is analyzed for Brix, sugar content, pH, and viscosity using inline sensors and laboratory instruments. Based on this analysis, adjustments are made by adding water, sugar syrup, citric acid, or fruit concentrates. If the product is to be marketed as nectar or a mango beverage rather than pure juice, the ratio of mango content to added water is adjusted accordingly. Throughout this blending stage, high shear mixers are used to ensure all components are thoroughly and evenly incorporated. With the base juice now standardized, it moves on to pasteurization. The juice is pumped through a heat exchanger where it is rapidly heated to between 85 and 95 degrees Celsius for a precise duration, typically around 30 seconds, to deactivate enzymes and eliminate any microbial contaminants. The pasteurization temperature and time are tightly controlled, using automated sensors that adjust flow speed and heating elements based on real-time data. After heating, the juice is flash-cooled using a counterflow plate exchanger, bringing it down to bottling temperature, typically just a few degrees above ambient. Before packaging, the juice may undergo deaeration. Mango juice, due to its thickness and high natural sugar content, is prone to oxidation, which can alter color and flavor. In a vacuum deaeration chamber, the juice is exposed to low pressure, causing dissolved oxygen and other gases to be removed. This protects the flavor and extends shelf life. For products labeled as "with mango aroma" or for high-end juice lines, a flavor recovery system is also employed. During pasteurization and pulping, volatile aroma compounds are captured from the evaporated vapors, condensed, and stored in small tanks. These aromas are then reintroduced into the juice at controlled concentrations to restore the characteristic fruity bouquet. At this stage, the mango juice is fully prepared and ready to be packaged. The packaging hall is a high hygiene zone with controlled air filtration, often operating under positive pressure to keep contaminants out. Empty bottles or cartons are first sterilized using ultraviolet light, steam, or hydrogen peroxide mist. These containers move into a filling carousel where the juice is dispensed into each unit using volumetric or gravity fillers. Sensors ensure that each container is filled to the exact target level, and any discrepancies are immediately rejected by the control system. After filling, bottles are capped or sealed and sent through a cap sterilization tunnel to eliminate any surface bacteria introduced during capping. Each sealed unit is then passed through a coding station where laser or inkjet printers mark the label or neck with production dates, expiry dates, and batch numbers. The bottles are labeled using high-speed machines, which apply adhesive or shrink-wrap labels depending on the format. A visual scanner confirms that every container is correctly labeled and marked. Any mislabeled bottles are rejected into a separate collection chute for reprocessing. Once labeled, the bottles are grouped into packs, shrink-wrapped, and moved to an automated palletizing system. Robotic arms arrange the bottles into patterns on wooden or plastic pallets, optimizing for stability during storage and shipping. Each pallet is then wrapped with stretch film, weighed, and tagged with a tracking barcode. These barcodes are linked to a centralized inventory system that records every detail of the product's production, packaging, and quality control data. This enables full traceability from the factory to the retailer. Before shipping, the pallets are stored in temperature-controlled warehouses. Mango juice, especially when not preserved with artificial additives, is sensitive to heat and light, so storage areas are kept cool and protected from UV exposure. During storage, samples from each batch are periodically tested for microbiological stability, pH drift, sugar degradation, and visual clarity. These checks ensure that the product maintains its intended quality over time. Any deviation prompts an investigation and can trigger a hold on the affected batch. Finally, when orders are placed, the pallets are scanned, retrieved by automated guided vehicles or forklifts, and loaded into refrigerated trucks. Logistics systems plan delivery routes and timing to maintain cold chain integrity, ensuring the mango juice reaches distribution centers, supermarkets, or export terminals without temperature fluctuation. Throughout this entire process, factory systems continuously log data, temperatures, flow rates, batch compositions, and equipment performance to ensure complete quality assurance and compliance with regulatory standards. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of litres of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 litres in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple-effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per litre. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in two operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. The process of making Pepsi begins with one of its most essential components: water. Water forms the majority of the final beverage, making its purification and preparation one of the most critical steps in the manufacturing process. PepsiCo takes extreme care in sourcing and treating water to ensure the final product is free from impurities, contaminants, and off flavors. Without this careful preparation, the beverage could have inconsistencies in taste, appearance, and carbonation retention. The journey starts with sourcing water from natural springs, municipal supplies, or underground wells, depending on the bottling plant's location. However, regardless of its origin, This water must go through extensive treatment to meet PepsiCo's strict quality standards. The process begins with initial screening, where water passes through coarse filters that remove large particles such as dirt, sand, and debris. This is followed by sedimentation, a method that allows heavier impurities to settle at the bottom while the cleaner water moves forward in the process. Once the larger impurities are removed, the next step is carbon filtration. This step is crucial for removing chlorine, organic compounds, and any unwanted odors or tastes that could interfere with the Pepsi formula. Activated carbon filters contain a highly porous material that traps chemical impurities while allowing pure water to flow through. This process not only improves the taste of the water, but also enhances its ability to mix well with the other ingredients later in production. But up next is the reverse osmosis process, one of the most advanced purification techniques used in beverage manufacturing. Reverse osmosis involves forcing water through an ultra-fine membrane under high pressure, effectively removing even the tiniest dissolved particles, including salts, minerals, and microscopic contaminants. This ensures that the water is as pure as possible before it becomes part of the Pepsi formula. To further refine the water, it undergoes ultraviolet sterilization. This step is essential for eliminating any remaining bacteria, viruses, or other microorganisms that could compromise the safety and shelf life of the beverage. High-intensity UV light disrupts the DNA of these microorganisms, rendering them inactive without the use of chemical disinfectants. Finally, before the purified water is stored, it goes through an ozonation process. Ozone, a highly reactive form of oxygen, is injected into the water to act as a natural sanitizer. This step ensures that the water remains free from microbial contamination while it is held in large stainless steel storage tanks, awaiting the next phase of production. Now that the water has been meticulously purified, it must be precisely balanced to create the ideal base for Pepsi. Even though reverse osmosis removes most dissolved solids, a controlled amount of specific minerals is added back into the water to optimize taste and improve its ability to retain carbonation. This step is carefully monitored as the mineral composition of the water can impact the final mouthfeel and texture of the beverage. With the water fully prepared and stored in sanitary tanks, it is now ready to be mixed with the other key ingredients that will give Pepsi its distinctive flavor. But before moving on to mixing, each batch of purified water is rigorously tested for quality. Samples are taken from the storage tanks and analyzed in PepsiCo's in-house laboratories. Scientists and quality control experts measure pH levels, mineral content, and overall purity, ensuring that each batch meets the company's global standards. If any irregularities are detected, the water is either reprocessed or discarded, preventing any inconsistencies from affecting the final product. Now that the water has been meticulously purified and stored in sanitized tanks, the next crucial step in the Pepsi manufacturing process is the preparation and addition of sweeteners. Sweeteners play a fundamental role in defining the flavor profile of Pepsi, contributing to its signature taste while also affecting mouthfeel, viscosity, and overall balance. The selection, processing, and precise blending of these sweeteners are critical to ensuring that every bottle and can of Pepsi maintains consistency across different production facilities worldwide. In most regions, Pepsi is sweetened with high fructose corn syrup, a liquid sweetener derived from cornstarch. However, in some markets, particularly in countries where cane sugar is more widely available or preferred, sucrose from sugarcane or sugar beets is used instead. Regardless of the source, the sweetener must be carefully refined and processed before being added to the beverage. The journey of high fructose corn syrup begins with corn milling, where harvested corn is cleaned, steeped, and ground into a slurry to separate the starch from the fiber, protein, and germ. The extracted starch is then subjected to enzymatic processing, where it is converted into glucose. A second enzyme is introduced to transform a portion of the glucose into fructose, increasing its sweetness. The result is a thick, viscous syrup that is then further refined, filtered, and tested to ensure the correct balance of glucose and fructose. The most commonly used variety in soft drinks is HFCS 55, which contains approximately 55% fructose and 45% glucose, closely mimicking the sweetness profile of cane sugar. For regions that use sucrose instead of HFCS, the sugar is derived from either sugarcane or sugar beets. Sugarcane is harvested, crushed to extract juice, and then boiled to concentrate the sugar, forming crystallized sucrose. Sugar beets, on the other hand, are sliced and soaked in hot water to extract sugar, which is then purified and crystallized. In both cases, the raw sugar undergoes extensive refining to remove impurities and ensure a uniform, pure sweetener. Once the sweetener is ready, it must be dissolved into a concentrated syrup before being mixed with other ingredients. In a dedicated mixing tank, the high fructose corn syrup, or dissolved sucrose, is blended with purified water in precise proportions to create a uniform, sweetening solution. This syrup is continuously agitated to prevent crystallization and ensure a consistent texture. To maintain Pepsi's exact sweetness level, refractometers are used to measure the syrup's sugar concentration, ensuring it falls within the specified range. At this stage, the syrup is also subjected to rigorous quality control testing. Laboratory technicians take samples from each batch and analyze them for purity, consistency, and microbial safety. Any inconsistencies in sweetness or viscosity could alter the taste of the final product, so adjustments are made, if necessary, before moving on to the next step. Now that the sweetener has been perfectly prepared, it is time to introduce the key flavoring components that define Pepsi's distinctive taste. Pepsi's flavor is the result of a complex blend of natural and artificial flavorings, including citrus oils, spice extracts, and caramel notes. The exact recipe remains a closely guarded secret, known only to a select few within the company. But it is widely understood that ingredients like orange oil, lemon oil, vanilla, cinnamon, nutmeg, and cola nut extract contribute to the drink's signature profile. The flavoring components are carefully blended into a concentrated mixture known as the flavor base. This highly concentrated liquid is prepared in a separate, sterile mixing tank, where precise measurements of each ingredient are combined under controlled conditions. Some of these ingredients, particularly the essential oils, must be emulsified using stabilizers to ensure they mix properly with the water-based formula of Pepsi. Without proper emulsification, the oils could separate from the rest of the beverage, leading to inconsistent flavor distribution. Phosphoric acid is then added to the flavor base, providing Pepsi with its signature sharpness and tangy aftertaste. This acid also plays a crucial role in preserving the beverage by inhibiting microbial growth. The level of acidity is carefully controlled to balance the sweetness of the drink and enhance its overall flavor. Caramel color, which gives Pepsi its deep brown hue, is another essential ingredient added at this stage. This colorant is created by heating sugar compounds under controlled conditions, resulting in a stable and safe coloring agent. The intensity of the caramel color is strictly regulated to ensure that every bottle of Pepsi has the same visual appeal. Once the flavor base is complete, it must be thoroughly mixed with the sweetener solution to create the final syrup that will be used in the soft drink. This blending process takes place in large stainless steel tanks, where high-powered mixers ensure even distribution of all ingredients. The proportion of sweetener to flavor base is precisely measured, as even a slight deviation could alter the taste of the final product. Before the syrup is approved for use, samples are taken and analyzed in a quality control lab. Tests include pH measurement, viscosity checks, and sensory evaluations, where trained tasters confirm that the syrup matches Pepsi's standard flavor profile. These rigorous quality checks ensure that every batch of syrup is identical, maintaining Pepsi's global consistency. Once the syrup has passed all quality control tests, it is stored in temperature-controlled holding tanks, ready to be mixed with carbonated water. These tanks are kept under strict sanitary conditions to prevent contamination and preserve the integrity of the syrup. But up next is one of the most critical aspects of the Pepsi production process: carbonation. This step is responsible for the effervescence and refreshing sensation that consumers associate with soft drinks. Without proper carbonation, Pepsi would lose its signature fizz, altering the drinking experience. The process of infusing the beverage with carbon dioxide is both a science and an art, requiring precise control over temperature, pressure, and gas concentration. To begin the carbonation process, purified water is first chilled to near freezing temperatures. The reason for this is that carbon dioxide dissolves more efficiently in cold water than in warm water, ensuring maximum carbonation retention. The chilled water is then injected with high purity CO2 gas under controlled pressure, creating carbonated water. This water is then carefully blended with the pre-mixed syrup in an exact ratio, typically around 5 parts carbonated water to 1 part syrup. The precise proportion ensures the correct balance of flavor, sweetness, and fizziness in the final beverage. Maintaining the right level of carbonation is crucial, as it directly affects the mouthfeel and shelf life of the product. If the carbonation is too low, the drink will taste flat and less refreshing. If it is too high, the beverage may be overly acidic or cause excessive foaming during packaging. To ensure consistency, carbonation levels are continuously monitored using pressure sensors and dissolved CO2 analyzers. The newly carbonated Pepsi must now be handled carefully to prevent the loss of carbonation before packaging. At this stage, the beverage is kept under constant pressure in specialized holding tanks to maintain CO2 solubility. Any sudden release of pressure could cause the carbon dioxide to escape, resulting in a less fizzy drink. With the Pepsi now fully mixed, carbonated, and held under precise pressure conditions, the next step is bottling and packaging. This is one of the most intricate parts of the manufacturing process, requiring extreme precision, speed, and cleanliness to ensure that every bottle and can of Pepsi is filled, sealed, and prepared for distribution without losing carbonation or quality. The bottling process must take place in a sterile environment to prevent contamination, and the machinery involved operates at incredibly high speeds to keep up with global demand. The first part of this process involves the preparation of bottles and cans. Pepsi is available in a wide range of packaging formats, including glass bottles, aluminum cans, and plastic bottles made from polyethylene terephthalate. Each type of container has its own preparation requirements, but all must be thoroughly cleaned and sterilized before being filled. For plastic bottles, the process begins with small, preformed PET molds called preforms. These preforms are heated to a specific temperature and then rapidly inflated using high-pressure air inside a blow molding machine. This machine expands the preforms into their final bottle shape, ensuring uniform thickness and durability. The freshly molded bottles are then conveyed into a high-speed rinsing station, where they are thoroughly washed with filtered water and food-safe sanitizing agents to remove any potential contaminants. Glass bottles undergo a more rigorous cleaning process since they are often reused. They are first soaked in a high-temperature caustic solution to break down any residue from previous use, followed by multiple rinses with clean, filtered water. Finally, they pass through a steam sterilization chamber to ensure that no microorganisms remain. Aluminum cans, on the other hand, arrive at the bottling plant pre-formed and ready to be filled. However, before filling, they are sent through a high-pressure air jet cleaning system that blasts away dust and debris. Since aluminum cans are highly sensitive to corrosion, a thin food-safe lining is applied inside each can to prevent any reaction between the beverage and the metal. Now that the bottles and cans are fully prepared, the filling process can begin. The carbonated Pepsi is transported through a network of pressurized stainless steel pipes that maintain the beverage's optimal CO2 concentration and temperature. The filling machines operate at high speeds, capable of processing thousands of containers per minute. For PET and glass bottles, filling is done using gravity-based or counter-pressure filling systems. In a counter-pressure system, the bottle is first pressurized with CO2 before the Pepsi is introduced. This prevents foaming and excessive carbonation loss during filling. The precise amount of liquid is dispensed into each bottle, with sensors ensuring that no underfilled or overfilled bottles proceed down the production line. Aluminum cans require a slightly different approach. Since they are more prone to CO2 loss due to their wide openings, the filling nozzles are designed to minimize turbulence as the liquid enters. The cans are quickly filled and then topped with a small injection of nitrogen gas to prevent oxidation before being sealed. Now that the containers are filled with carbonated Pepsi, the next critical step is sealing. This process must be done immediately after filling to prevent carbonation loss and contamination. For plastic and glass bottles, this involves capping. Screw-on plastic caps are applied to PET bottles using high-speed rotary capping machines, which tighten each cap with precise torque to ensure a secure seal. Glass bottles, often used for premium or international markets, are sealed with either metal crown caps or twist-off caps, depending on the region. Aluminum cans are sealed using a double seaming process. A lid, which contains an integrated pull tab, is placed on top of the can and then mechanically crimped around the rim. This creates an airtight seal that locks in carbonation and prevents leakage. With all the containers now sealed, they move on to the quality control phase. At this stage, random samples are pulled from the production line and tested for multiple factors, including fill level, carbonation retention, pressure stability, and contamination. Advanced X-ray and laser scanning systems inspect each bottle and can to ensure that there are no foreign particles, dents, or defects in the packaging. Any defective units are immediately rejected and removed from the batch. Once the beverages pass quality control, the containers proceed to labeling. Each bottle and can receives a label that includes branding, nutritional information, ingredient lists, and regulatory compliance markings. PET bottles have labels applied using heat shrink or pressure-sensitive label machines, while aluminum cans typically have their designs pre-printed onto the metal surface. After labeling, the bottles and cans are grouped into multi-packs for retail distribution. This process involves bundling them into various configurations, such as 6-packs, 12-packs, or full cases. Plastic shrink wrap, cardboard trays, or molded carrying handles are used to secure the multi-packs for easy transportation. The completed packs are then stacked onto pallets in an organized manner and wrapped in stretch film to stabilize them for shipping. Now it's time for one of the most logistically challenging aspects of Pepsi production: distribution. The pallets of finished Pepsi products are moved to temperature-controlled warehouses where they are stored before being shipped to retailers, grocery stores, vending machines, and restaurants. Since Pepsi is produced in enormous quantities to meet global demand, distribution logistics must be precisely managed to ensure that every store and vendor receives fresh products. Pepsi's supply chain is a highly coordinated operation involving fleet management, refrigerated storage, and just-in-time delivery systems. Large distribution centers act as hubs where shipments are sorted based on region and customer demand. Trucks, rail transport, and even cargo ships are used to move massive volumes of Pepsi across countries and continents. Once the products arrive at their final destinations, they are placed in cold storage or directly onto store shelves. In grocery stores and supermarkets, Pepsi is often stored in temperature-controlled sections to maintain freshness. Restaurants and fast food chains receive large volumes of Pepsi in bulk containers, which are connected to soda fountains for on-demand dispensing. Throughout this entire process, PepsiCo maintains strict inventory tracking and quality assurance programs. Each batch of Pepsi is assigned a unique tracking code, allowing the company to trace products back to their production date, location, and ingredient sources. This ensures that in the event of a recall or quality issue, affected products can be quickly identified and removed from circulation. With the Pepsi bottles and cans now filled, sealed, labeled, and packed for distribution, one of the final but most crucial aspects of the manufacturing process is ensuring product consistency, longevity, and consumer satisfaction. Maintaining Pepsi's signature taste and quality across millions of bottles and cans requires an advanced system of quality control, storage optimization, and packaging innovation. Every aspect, from the shelf life of the product to the materials used in packaging, plays a role in ensuring that each Pepsi delivered to a consumer is as fresh and enjoyable as the last. The first key factor in Pepsi's shelf life and consistency is its ability to retain carbonation over time. Carbonation, which gives Pepsi its signature fizziness, is created by dissolving carbon dioxide into the liquid under high pressure. The challenge is ensuring that this CO2 remains trapped within the beverage from the moment it is bottled until it is opened by the consumer. To maintain carbonation, Pepsi uses specially designed bottles and cans that act as airtight barriers, preventing CO2 from escaping. Plastic bottles made from polyethylene terephthalate are engineered with multiple layers that slow down gas diffusion, preventing CO2 from seeping out over time. The thickness and structure of PET bottles are carefully optimized to balance durability with weight, ensuring that the bottles are strong enough to retain carbonation while remaining lightweight for transportation. Aluminum cans provide an even better barrier against gas loss. Their completely sealed structure ensures that no CO2 escapes, preserving the drink's fizziness for extended periods. Additionally, a protective food-grade lining inside each can prevent any reaction between the metal and the beverage, which could otherwise affect flavor. Glass bottles, often used for premium markets or limited edition versions of Pepsi, offer the best gas retention of all packaging types. Glass is completely impermeable, meaning that Pepsi stored in glass bottles maintains its carbonation for the longest period. However, glass is heavier and more fragile than plastic or aluminum, making it less practical for mass production and distribution. Another critical factor in product longevity is preventing oxidation. Exposure to oxygen can alter the taste of Pepsi, causing it to become flat and develop off flavors over time. To counter this, PepsiCo employs nitrogen dosing in certain packaging lines. This process involves injecting a small amount of nitrogen gas into PET bottles just before sealing. The nitrogen displaces any residual oxygen inside the bottle, reducing the risk of oxidation while also adding structural rigidity to the bottle, preventing it from collapsing under vacuum pressure. Beyond carbonation and oxidation control, preservatives also play a role in maintaining Pepsi's freshness. While the beverage's acidity and carbonation naturally inhibit microbial growth, additional preservatives such as sodium benzoate are included to extend shelf life further. These preservatives prevent mold, yeast, and bacterial growth, ensuring that Pepsi remains safe for consumption for months or even years after production. Now that the beverage's stability is secured, it must be stored and transported under optimal conditions. Pepsi is highly sensitive to temperature fluctuations, which can affect carbonation retention and overall flavor. As a result, warehouses, distribution centers, and retail storage areas are kept within a controlled temperature range to prevent heat exposure. Excessive heat can accelerate CO2 loss in plastic bottles and increase oxidation reactions, leading to a flatter, less refreshing drink. To counteract this, refrigerated warehouses are used in regions where high temperatures could compromise product quality. During transportation, trucks equipped with climate control ensure that Pepsi is not exposed to extreme heat or direct sunlight, both of which could degrade the beverage. Another major factor that affects Pepsi's taste consistency is the impact of light exposure. Ultraviolet light can break down some of the organic compounds in Pepsi's flavoring, leading to unwanted taste changes. This is why Pepsi bottles, particularly those made from PET, are designed with tinted or opaque plastic to reduce UV penetration. Aluminum cans and glass bottles naturally provide complete light protection, further ensuring product stability. Once Pepsi reaches its final retail destinations, whether in grocery stores, vending machines, or fast food chains, it is crucial that storage guidelines continue to be followed. Retailers are instructed to keep Pepsi stock rotated, ensuring that older products are sold first and newer shipments are stored properly. This helps maintain product freshness for consumers while preventing expired stock from sitting on shelves. Fast food chains and restaurants that serve Pepsi from soda fountains have additional steps to ensure taste consistency. Instead of pre-packaged bottles and cans, Pepsi is delivered to these locations in large pressurized syrup containers known as bag-in-box systems. These containers hold concentrated Pepsi syrup, which is mixed with carbonated water on demand through specialized dispensing machines. The bag-in-box system allows for efficient storage and prevents waste, as restaurants can control the syrup-to-water ratio for optimal taste. These systems are regularly maintained, with filters and carbonation settings adjusted to match the ideal flavor profile. Additionally, PepsiCo provides restaurants with quality control tools to measure CO2 levels and syrup concentration, ensuring that every poured glass tastes as good as a bottled Pepsi. With all these measures in place, Pepsi is now fully ready for consumers to enjoy. But beyond the immediate production and distribution, PepsiCo continually invests in research and development to improve manufacturing efficiency, sustainability, and packaging innovations. One of the company's most significant focuses in recent years has been reducing the environmental impact of its packaging. PepsiCo has made major advancements in recyclable PET bottle technology, developing bottles that contain post-consumer recycled plastic to cut down on waste. Additionally, the company has experimented with plant-based PET alternatives that reduce reliance on petroleum-based plastics. Aluminum cans have also been a major target for sustainability improvements. Since aluminum is highly recyclable, PepsiCo has worked to increase the amount of recycled aluminum used in can production. The company encourages consumers to participate in recycling programs, ensuring that cans are properly collected and reused. In some markets, PepsiCo has even introduced refillable glass bottle programs, allowing consumers to return used bottles for sanitation and reuse, significantly cutting down on single-use waste. Further technological advancements in bottling machinery have also improved efficiency in the production process. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate-making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120-140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink-wrapped using rotating arms or heat tunnels, and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution. Whether headed to a supermarket distribution center, a specialty retailer, or international export, the chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. CAFE practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under CAFE practices, the beans are harvested, typically by hand. Hand picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh-scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill-seal systems for smaller bags and horizontal form fill-seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple, water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, The glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, The sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs. using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios.